Good day, everyone, and this is Learn with Mike. So, for today's topic, it's about ideal gas law. Let's start. Aside from pressure, volume, and temperature, moles may also be combined to the three properties of gases to establish the relationship among the four variables affecting the behavior of gases. Boyle's, Charles, Gay-Lussac's, and Avogadro's laws, when combined, constitute to what we call ideal gas law. So going back to combined gas law, it is only the combination of Boyle's, Charles, and Gay-Lussac's. But for ideal gas law, we're going to combine the four laws, which are the Boyle's, Charles, Gay-Lussac's, including the Avogadro's number or Avogadro's law. So ideal gas law. It is based on the experimental measurement of the physical properties of gases, temperature, pressure, volume, and the number of moles. It states that the volume of a gas varies directly with the number of moles and absolute temperature in Kelvin scale and inversely proportional with the pressure. So for the ideal gas law, we use this equation or formula. P V is equal to nRT, where P is the pressure, V is the volume, N is the number of mole, T is the temperature, and R is the proportionality constant at STP. So when we say STP is standard temperature pressure, so later I will explain what is STP. And the value of R is 0.0821 liter ATM over mole Kelvin. And take note, temperature is always in Kelvin scale. The difference of this formula is that in our previous laws, we have P1, V1 or V1, V2. But in this case, we don't have initial or final quantities. Okay, so when we talk of STP or standard temperature and pressure, it has a certain value. So for the temperature, the value in STP is 273.15 Kelvin, or this is equivalent to 0 degrees Celsius. And for the pressure, we have many values. So it can be 760 torr, 760 millimeter Hg, 76 centimeter Hg, and 1 atm. So I have video about the four units, which are the volume, temperature, pressure, and the number of moles. I have many values there for pressure, so just check it out. Now, let's have an example problem. 6.5 moles of carbon dioxide gas are present in a container with a volume of 31.5 liters. What is the pressure of this gas in ATM if the temperature is 65 degrees Celsius? Okay, so let's solve. The given V1 is 31.5. The number of mole, which is N, is 6.5 moles. Temperature is 65 degrees Celsius. And always, because we have R that is constant, so 0.0821 liter ATM over mole that Kelvin. So the unknown is the pressure. So before we start, let us first convert temperature scale to Kelvin, Celsius scale to Kelvin. 273.15 plus 65 is 338.15. Now let's solve because the values are now complete. So PV over N is equal to nRT. Substituting the value, so P times 31.5 is equal to 6.5 times 0.0821 times 338.15. So from here, we can cancel some of the units. So we cancel mole and Kelvin. Then the remaining unit is liter ATM. Then we multiply. So 6.5 times 0.0821 times 338.15 is equal to 180.4537475 liter ATM. I suggest if you are in the middle of the computation, you copy all the values. Okay, and then for the left side, copy P and 31.5 liters. Then to find P, divide both sides by 31.5 liters. Cancel the unit liter on the right side. Then divide 180.4537475 to 31.5. Then P is equal to 5.73 atmosphere. Next problem. How much space will 5 moles of sulfur hexafluoride occupy if the temperature and pressure of the gas are 125 degrees Celsius and 8.5 atmosphere respectively. So write the given. N is 5 moles, T is 125 degrees Celsius, pressure is 8.5, and R is 0.0821 liter ATM over mole Kelvin. So the unknown is the volume. So converting temperature to Kelvin, 273.15 plus 125 is equal to 398.15 Kelvin. So the formula, substituting the value, so 8.5 ATM times V is equal to 5 times 0.0821 times 398.15. Canceling some of the units, multiplying the right side, so 5 times 0.0821 times 398.15 is equal to 163.440575. Then copy 8.5 ATM and V to the left. Then dividing both sides by 8.5 ATM, cancel, divide numbers to the right, 163.440575 to 8.5, then volume is equal to 19.23 liters. Next problem. A sample of helium occupies 10 liters of space at STP. So take note, at STP or standard temperature pressure, how many moles of helium are present in the sample? So the given volume is 10 liters and we have R always, which is 0.0821 liter ATM over mole dot Kelvin. And because we talk of STP, these are the values. For temperature, 273.15 Kelvin, and pressure is 1 ATM. And the unknown is the number of mole. So from here, no need to convert temperature from Celsius to Kelvin because it is already in Kelvin at STP. So solution, writing the formula, substituting the values, so 1 ATM times 10 liters is equal to N times 0.0821 liter ATM over mole Kelvin times 273.15 Kelvin. So multiply 1 times 10, or first we cancel K, then 1 times 10 is 10 ATM liters, then multiply 0.0821 times 273.15, that is 22.425615 liter ATM over mole. Next, to find N, divide both sides by 22.42565 liter ATM per mole. If you're wondering why the unknown is on the right side, because the usual is the unknown quantity is on the left side. It's okay. It's just the same. So cancel 22.42565, and then on the left side cancel ATM liter, so the remaining unit is mole. So 10 divided by 22.42565 is equal to 0.45 mole. Okay, so I guess this is the last example. A sample of 6 moles of sulfur hexafluoride, always sulfur hexafluoride, is present in a container with a volume of 22.4 liters. What is the pressure of the gas in atmosphere if the temperature is 130 degrees Celsius? So writing the given, V is equal to 22.4 liters, N is 6 moles, temperature is 130 degrees Celsius, R is equal to 0.0821 liter ATM per mole Kelvin. Unknown is the pressure. So writing the before we write the formula, let us first convert temperature to Kelvin, Celsius to Kelvin. 273.15 plus 130 is 403.15. Then, so let's substitute the value. So P times 22.4 is equal to 6 mole times 0.0821 liter ATM per mole over mole Kelvin times 403.15 Kelvin. Canceling some of the units, the remaining units are liter and ATM. So multiply 6 times 0.0821 times 403.15, the answer is 198.59169 liter ATM. Then copy P, 22.4 liters on the left side. Then to find pressure, divide both sides by 22.4 liters. Cancel. So 198.59169 over 22.4. Then pressure is equal to 8.87 atmosphere. Okay, so thank you for watching. I hope you learn. Subscribe if you learn. Thank you.